Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, so today we're very pleased to have Everett Howe visiting us from CCR, Center for Communications Research. And Everett and I have a long history together. I actually went to the University of Michigan to be a postdoc there so that I could have the opportunity to work with Everett, who was an assistant professor there at the time, just in time for him to leave before I arrived. But luckily, we've caught up with each other later and collaborated on various projects. Everett is an expert on abelian varieties and polarizations, among other things. And today he will speak to us on Genus-2 curves with a given number of points.
Thank you, Kristin, and thanks for the invitation again for coming here. It's a real pleasure to visit Microsoft, and I'm even happier to get some snow. It's been a long time since I think Michigan was the last time that I had some snow. So this is essentially the second part of Peter's talk, and he had the harder task of trying to explain the non-existence result, the lower bound result. And I have the easier task, I think, of explaining how we can solve an easier problem. So let me start. So again, the title is Genus-2 curves with a given number of points. Oops. And the genesis of this question, as Peter explained, is an easier question. Given some integer n, construct an elliptic curve, some E over some finite field, with n points. And this was solved in Rayner's thesis. There's this efficient algorithm that heuristically one expects will produce such an elliptic curve over a finite field in time polynomial in log n. So that's good. But you can think of ways of generalizing this question. And what Peter talked about was something hard. So given n, construct some curve C over some finite field, say of genus-2, with the number of points on the Jacobian of C equals n. And as it turns out, the only ideas we had for doing this, kind of the obvious generalizations of Rayner's method, were too hard. So this was too hard to get a nice polynomial time solution. And in fact, I think the most efficient method that we know of for solving this is to pick a prime Q of the right size and pick a genus-2 curve over that field and hope that the Jacobian has the right number of points, which is not a very satisfying algorithm. I think that's worse, I think. Yes?
Can you even count the number of points in the Jacobian efficiently?
That may be hard, but you can check to see whether there are n. So if n is, for instance, square free, then you could take a random point on the Jacobian and multiply it by n and see if the point is killed by that. So you actually could do this fairly efficiently, the testing the Jacobian part, but the whole algorithm of picking things at random is not advisable.
Are you assuming you have the factorization of n?
Assuming you have the factorization of n, maybe assuming n is square free. There are assumptions, but there's a third question. It's another way of generalizing the first question, which is to construct some C of genus-2. And this time, you don't ask for properties of the Jacobian, you just ask for properties of the curve. You want the curve to have n points. And this is what I'm going to talk about. So The idea that we initially had, so I should say this is the joint work with Peter and with Kristin. The idea that we initially started up with was, as in Peter's talk, we want to see if we can find some degree 4 field. So this is a totally imaginary quadratic extension of a totally real quadratic extension of Q. And we want to see whether we could find some element in this field that will be the Frobenius for our curve. So we would like K to be small in some sense so that we could compute Igusa class polynomials for it. We would like pi times pi bar to be probably a prime. If it's a prime power, that'll work, but it's never going to happen in practice. And we would like the number of points on C. That's going to be Q plus 1 minus the trace of pi. So that should be the number n that we are given. So you could write down what all these conditions mean, and then you could try to think of ways of constructing small fields with these properties. And we did that, and we had no good ideas. Everything was just too hard to control all of the things that we had to control. So we were kind of stuck. And that was very disheartening, because we thought this would be an easier problem, and then we were stuck. Until we had the clever idea that we should cheat. The whole problem was dealing with these quartic fields. It was, they're kind of hard to deal with. Saying what it means to be small for these fields is, not trivial. And instead, we had the idea of, instead of having the characteristic polynomial of Frobenius be an irreducible polynomial that defines a quartic field, we thought, what if we had the characteristic polynomial of Frobenius factoring? What if it factored as the product of two characteristic polynomials of elliptic curves over FQ? What would happen then? Well, then, if we could construct a curve whose Jacobian had this characteristic polynomial, then the number of points on the curve, which we would like to be n, would actually be equal to Q plus 1 minus the trace of this factor minus the trace of that factor. So our idea now is going to be to find two elliptic curves over FQ so that their traces satisfy this condition. And essentially what we want to do is to take two elliptic curves and glue them together. So take two elliptic curves and glue them to get a genus-2 curve. So later on in the talk, I'll expand this outline. I'll tell you how we can choose these curves over some finite field so that the traces add up to the right number. But before I get to that point, I want to talk a little more about this general idea. In fact, I think in the abstract that I sent out, I said that the talk would be kind of about gluing together curves and various applications. So one application is going to be solving this problem, almost solving this problem. Solving this problem 5/6 of the time. So, the reason I want to talk about this is it's a very old idea. Although maybe it's a little bit of a lie to say that it's a very old idea. I would like to say that people have been doing this for 180 years, but that's not exactly true. What people have been doing for 180 years have been the opposite. Breaking genus-2 curves into a product of elliptic curves. So let me review some of the history of this idea of finding a genus-2 curve whose Jacobian has two factors, has elliptic factors. So I'm going to start with a slide. So here is, well, the author is missing. Here is, oh, the author is still missing. This is Legender's, oh, there it is. Legender's, this is the third supplement to his treatise on elliptic functions, which was printed in 1828. So that's the 180-year thing. And at the very end of his treatise on elliptic functions, he talks about ultra-elliptic functions. And so what he's concerned about here is, as people were, is computing the values of integrals. So what he notes, maybe I'll write this on the board as well. What he notes is that if you're trying to compute the integral of dx over the square root of x, 1 minus x squared, 1 minus k squared, x squared. And he has limits of integration, but let's not worry about them. He says what you should do is make a substitution. And actually, you'll notice, well, let me write the substitution first. He says take p to be that. But in fact, you notice that he says something else. He forgets the k there. Something must have happened to the TeX file on the way to the printer. But if you do this, if you make the substitution, then this integral that has a degree 5 polynomial on the bottom, underneath the square root sign, turns into something involving these elliptic integrals. I don't know how clearly you could see this, but now there's a linear term in p and then a quadratic term in p. So he shows that this ultra-elliptic integral can be written as the sum of multiples of two elliptic integrals. So this was interesting. This was 1828. Legendre. But then in 1832, Jacobi was writing a review of Legender's book, and the review was in Krell's journal. And it was actually kind of hard to find this article because it's a book review. People were referred in the literature to this work of Jacobi. And so you look in the index for this volume of Krell, and you find that there were a couple of papers by Jacobi in Latin. And so you look through them and remember your high school Latin and try to see anything involving split Jacobians, and you don't find anything. It's very frustrating. And in the index to the volume, they don't mention that he also wrote this book review. So you finally find the book review. And it's really interesting to read the introduction to the book review. It's very purple prose about the old Legendre. He was 80 years old, writing this treatise on elliptic functions, and then Abel comes in because Abel has invented this whole new generalization of elliptic functions, and it's very romantic. But in a postscript to his book review of Legendre's paper, Jacobi says, actually, this family of integrals that Legendre considers can be generalized. So maybe I will turn this off for a minute. And he says, look instead at integrals of the form dx over the square root of x. And see if I could get the notation correct. It's, I have to say, awful notation. It's x times 1 minus x times 1 plus a lowercase chi x, 1 plus lambda x, 1 minus lambda chi x. And not surprisingly, there are misprints in this paper involving these things. There are some times where the x's are gone and the chi's are gone. It's a mess. And you kind of have to know what the answer is before you can read this and figure out what he's saying. And what he says is, let's see. Well, the way we would look at what they're doing is we would say, consider the Genus-2 curve given by this polynomial. Oh, maybe I should say, if you take lambda equal to 1 and set chi equal to k, you'll get this special case. What we would say is that this genus-2 curve has an involution. You send x to lambda chi over x, and y goes to some kind of messy thing. But the point is, you could just see that there's an involution just by looking at this transformation. You see that the pole of this function at infinity gets sent to the pole at 0, and 0 goes to infinity. The Weierstrass point, I should say. The Weierstrass point at x equals 0 goes to the one at infinity, and vice versa. The one at x equals 1 goes to this one over here, and vice versa. And these two get swapped. So this Mobius function, Mobius transformation, takes the zeros and poles of this right-hand side to the zeros and poles of the right-hand side, and therefore it turns into an automorphism of the curve, an involution. And if you take this genus-2 curve and take the quotient of it by this involution, it turns out that the quotient is a genus-1 curve. So this gives you a degree 2 map from C down to an elliptic curve E. And so that's how we would understand why it is that an integral involving this degree 5 polynomial can be expressed in terms of sums of integrals involving degree 3 polynomials. That's where that comes from. So this family of integrals that Jacobi wrote about has this nice property that via quadratic transformations you can write them in terms of elliptic integrals. And in 1867, Königsberger, and in 1883, independently, communication was not as good back then as it might have been. Picard, they showed that Jacobi's family is complete in the sense that if you have any genus-2 curve that has a degree 2 map to an elliptic curve, it comes, it lies in this family. So any hyperelliptic integral that you can convert into a sum of two elliptic integrals via degree 2 transformations essentially comes from this family. Okay. So this is very old stuff having to do with polynomial substitutions, and I want to somehow get to Jacobians. And since between the 1820s and now there are the late 1800s, it seems natural to go via period matrices. So if you want to get to abelian varieties, you have to step through period matrices. And in 1884, this is another kind of roundabout story. Kowalewski published a paper in 1884 that she actually wrote in 1874, but it didn't get published for 10 years. And she cites unpublished work of Weierstrass, who describes the period matrices of any abelian, the period matrix of a curve, what did I say? A curve that gives rise to an abelian integral that can be reduced to an elliptic integral. So he says that if a curve gives rise to some abelian integral that you can write in terms of an elliptic integral, then its period matrix has a special form. So of course you can write different equivalent period matrices, but there is a period matrix of the form can be written, let's see, so you have, I'm going to write the full matrix. So you have the identity matrix on the left-hand side, and then you have a tau in the upper left-hand corner. You have stuff below and to the right of that tau. You have a rational number, a over n, and symmetric in the second spot over, and zeros everywhere else. And this n is related to the degree of the transformation which takes the abelian integral to an elliptic integral. So Kowalewski cited this result in this paper that was in limbo for 10 years, but didn't prove it. So it was in 1884 again that Poincaré proved it. And the special case where the genus of the curve is 2, let's see. And this was also Poincaré, I think. Oh, no, this was Picard. I'm sorry. Poincaré proved this, and then I believe it was Picard that proved in the Genus-2 case that if you write the period matrix in a slightly different way, so you, instead of having the identity, you do this anti-identity, you get tau 1, a tau 2, and a 1 over n, and a 1 over n. And in 1884, so Picard was not aware of this Weierstrass result until 1884 when this paper of Poincaré came out. And I think actually Poincaré saw Picard's paper and said, hey, this has already been done. It's just that the news didn't get spread very well. But in 1884, Picard was able to show that this result follows easily from Weierstrass's, even though Weierstrass has something which is not necessarily a 1 in the numerator. He shows that you can get a 1 in the numerator. So I might show something about that. Yes, it was Picard. So, right. Down there, you see the critical period matrix. Okay, that's enough for that for now. Okay, so what does all this mean in terms of elliptic curves and abelian surfaces? How would we understand it 100 years, more than 100 years later? So I'll write over here for a while. If we have this period matrix with a tau 1 and a tau 2 and a 1 over n and a 1 over n, let's look at the elliptic curve corresponding to this tau 1. So this is some lattice sitting inside of the complex numbers. And let's look at the other elliptic curve that corresponds to the lattice 1 tau 2 sitting inside of the complex numbers. And let's look at some n torsion points on these curves. So I'm going to let P1 be the n torsion point given by the class of 1 over n mod lambda. And I'm going to let Q1 be the n torsion point corresponding to tau 1 over n mod lambda. And over here we'll have a P2 and a Q2. And I need to get the notation right. I'm going to use the same idea, 1 over n and tau 2 over n. So then you could write a map from E1 times E2 to the Jacobian of this curve C, whose kernel is the group G that's generated by P1, Q2, and Q1, P2.
How is C defined?
C is going to be the curve with this period matrix. And you can kind of visibly see that in here there is a sublattice with tau 1 and tau 2 as the a sublattice that's the product of two one-dimensional lattices. So, and so if you kind of translate the stuff involving lattices and period matrices into abelian surfaces, this is what you get. And the swapping of the P1, the P's and the Q's here, is related to the fact that you've reversed the identity matrix here. And to make this even more modern, what we're saying is that given an isomorphism from the end torsion of an elliptic curve E1 to the end torsion of an elliptic curve E2, that anti-respects the Weil pairing. So that reverses the Weil pairing. So that anti-respects the Weil pairing. So I guess that means that if you take the Weil pairing, which I'll denote by little e, E2 of psi p psi q should be E1 of PQ inverse. Given such a thing, you get a diagram so here we have multiplication by n. And here we have the graph of psi, which is the kernel of the vertical map. So if you take this diagram and turn it on its side, you'll get this left-hand column. And if you take the dual of this map, you'll get this map. And Jacobians have these things called principal polarizations that will, in this case, map the Jacobian to itself, really to its dual. It'll fit in a diagram like this, where this is multiplication by n. So in some sense, this diagram and the words I just said are the kind of modern day translation of what this period matrix means. The fact that you could write the Jacobian with a period matrix of this form. Okay. So what all this is talking about, in some sense, then, is how, for a given integer n, there is some way, kind of some abstract way, that you could get to elliptic curves and produce a Jacobian. So the question is, the question we face now, since what we want to do to solve our original problem is we want to find two elliptic curves over a finite field, and I still have to say how we're going to find those curves. But once we've found them, we want to find a Jacobian that is isogynous to the product. And this family of constructions, depending on n, is going to give us a family of ways of doing that. And we'll only be able to use these constructions if they're actually constructions, if they actually can use things, write down equations to solve these problems. So let me turn now to the question of, given a value of n, can you actually write down equations of curves that will fit in a diagram like this? And the answer is yes, you can do that in certain cases. And I guess we've already seen one of those cases. So now we're moving from observing that some Jacobians can be broken apart to the problem of given two elliptic curves, how do you glue them together? So how explicit is this? So it depends on the value of n. So if we look at the case n equals 2 first, I've already told you, I've written down this thing that Jacobi wrote down. But I would rather show you a different way as well. So this is, I think, simpler than Jacobi. It's at least something that I can remember, and that's saying something. Suppose you start with an elliptic curve E1 given by y squared equals x times x minus 1 times x minus lambda. And for now, I'm going to be working over an algebraically closed field. I don't want to worry about any arithmetic. I just want geometric stuff. And for E2, I'll take y squared equals x, x minus 1, x minus mu. So you can always write elliptic curves in this Legendre form. And suppose you let P1 be the point x equals 0, y equals 0. I'm sorry, x equals 1, y equals 0. And Q1 be the point lambda 0. And here I want to actually reverse the notation. So Q2 will be 1, 0, and P2 will be mu 0. So how do you take this data and produce the curve C that is supposed to exist? It's very easy. So I propose that that is easy enough to remember. And you actually see that there are going to be some exceptional cases from this. So let me show you the exceptional case and then say what happens when you do care about arithmetic and not just geometry. So the exceptional case is going to happen when this right-hand side has multiple roots. That would be a bad thing because you wouldn't get a Genus-2 curve. So this will give you multiple roots if and only if lambda equals mu. Was that right? I believe that should be correct. If and only if lambda is mu. Because if lambda is mu, this will be a 1, and you'll have multiple roots there. And you'll also get multiple roots here as well. And if these two things are equal, then you cross multiply, and again you find that lambda equals mu. So what happens in that case, what happens in this diagram, the thing is that you get a principally polarized abelian surface down here, but it's not a Jacobian. And what happens is that left side becomes fits in a diagram where the right, what is the Jacobian there is actually E1 times E2 again, and the map is this map whose kernel has size 4. So instead of getting a simple principally polarized surface, which is a Jacobian, you get a reducible principally polarized surface, which is just a product of elliptic curves. And again, if lambda equals mu, then in fact E1 and E2 are the same elliptic curve. So the problem only comes up when you're trying to take an elliptic curve and glue it to itself by identifying the two torsion subgroup with itself. So that does seem like an exceptional case. So, okay. So that's kind of what is going on geometrically. And if you care about the arithmetic, if you want to have elliptic curves that are defined over some base field, then you can work out what happens. And geometrically, you're still doing this very simple thing, writing down an equation kind of like this, but it is a little more painful. And I'll just show you what you get. So this is from a paper that I wrote with Bjorn Poonen and Frank Leprevot. And so here, it's not even particularly worth going through, aside from the fact that you see that this thing, which is going to be the right-hand side of an equation for a genus-2 curve, has kind of complicated factors coming in that deal with your arithmetic, but it's still x squared plus something, x squared plus something, x squared plus something. So you can still see the traces of the geometry occurring, even though the arithmetic makes it more complicated. But the point is that it's very explicit. So you can, given these two elliptic curves and an identification of the two torsion groups, you can easily just write down the genus-2 curve that you get. So that's what the case n equals 2. The case n equals 3 is also fairly explicit, at least geometrically. So the case n equals 3. So in 1876, Hermite wrote down an example, a family of examples. He translated into modern terminology. He looked at x cubed, this family of genus-2 curves, and he observed that if you set u equal to 4x cubed minus 3x, you could express this right-hand side as a cubic function in u, so that this degree 5 polynomial in x, this y squared equals a degree 5, turns into y squared equals a degree 3 rational function in x, which gives you an elliptic curve. And likewise, you could also make a different substitution. 2x cubed minus b over 3x squared minus 1. And again, you could write this right-hand side as a cubic expression in v, which gives you, again, a different elliptic curve that this genus-2 curve maps to. So there's a one-parameter family, which is not enough parameters. And it was only in 1885 that Goursat kind of wrote the final answer. He said, look at this family of genus-2 curves where there's a condition. You need that this q should be 4 times b plus 4/3 ap. So it looks like there are 4 parameters, but really there's only 3. And really there's only 2 because you scale x and these parameters can be scaled as well. So really it's only a 2-parameter family, which is good. That's the right number. And now the substitutions that you use are even more related to the equations for the curve. So this is kind of the geometric picture again. It's not quite as simple as the geometric picture for the degree 2 examples, the n equals 2 examples, but it's still not that hard to write down. But as far as I know, no one has gone through the kind of painful details of working out the arithmetic that will make everything work over some fixed base field. But that actually won't matter for our application. So I'll get to our application. I might as well just show you the paper of Goursat. So here's an announcement of it, at least, from Compte Rendu in 1885. And Again, they're always talking about integrals. But you get this polynomial. I guess he's using t instead of x, but he gives the substitutions that you need to reduce that to elliptic integrals. So there's one of the substitutions I gave. So, okay. And I think that even might be all for the pictures. Okay. So then, you can look at higher ends. Bolza did some work for n equals 4, but I had been unable to decipher it. I've looked at the paper not terribly carefully, but I haven't been able to kind of extract nice parameterized families with degree 4 expressions in them. But it should be possible. For n equals 5, there's much more recent work. I actually haven't seen this, but from what I understand, Magard, Cheska, and Volklein have a paper where they explicitly write down the parameterized families of genus-2 curves that have degree 5 maps to elliptic curves. So, and that's as far as I believe anyone has gotten. Okay. So, okay, that was the historical digression. Let's go back to our original problem. So what we wanted to do was to construct a curve with a given number of points, and our idea was to write our n as q plus 1 minus s minus t, where s and t were traces of elliptic curves. And our algorithm for doing this, maybe now you'll understand why I waited so long to say it, because not only were we cheating by looking at split Jacobians, we're going to cheat even more. So step 1 is to find an elliptic curve over FQ with a number of points equal to n. So we use Raynier's thesis to produce a Q and an E, and whose trace is t, and that satisfies that relation. So we want to find a genus-2 curve that has n points. And now we have this elliptic curve with n points. So we have the right t here. The only way we can find another curve that will help us is if we find a curve with trace 0. So we want to find, okay, so now FQ is fixed. So we want to find some second elliptic curve, E prime over FQ, with trace 0, which is to say that the number of points on the curve should be q plus 1. And you might recall from Peter's talk that this was supposed to be a hard problem. Given a finite field, a particular finite field, finding an elliptic curve with a given trace is typically a very hard thing to do, unless the trace you're looking for is trace 0. And in that case, it turns out to be a very easy thing to do. If you write down a supersingular elliptic curve over this field, it will have trace 0, assuming q is a prime, which it most likely is. So it turns out to be very easy to write down curves of trace 0. So essentially what happens is that there is a particular elliptic curve in characteristic 0 over q that will be supersingular for half of all primes. And if that first one doesn't work, then there's another elliptic curve over q that's supersingular for half of all primes. And if that doesn't work, you try another one, and there are something like maybe 7, I forget how many. It's the number of class number 1 fields. So is it 11 fields or 11 discriminants?
9.
9, okay, yeah. So you have 9 choices already of elliptic curves defined over q that are likely to give you a supersingular curve. And if they don't, there are other things you could do. So it's not at all hard to find a supersingular elliptic curve. And once we do that, now we have an E and an E prime with the right number of points, with the right traces. If we can glue them together, then we will have solved this problem of constructing a genus-2 curve. So step 2 is going to be to glue. And here, there are actually going to be some problems. Because if we use the n equals 2 gluing, then what we need is an isomorphism between the 2 torsion of E and the 2 torsion of E prime. An isomorphism as groups with an action of the Galois group of the base field. And in particular, this will mean that the trace of each one, the 2 traces will be congruent to one another, modulo 2. And this S we already know is 0. So T is going to be an even number. And therefore, N, which is Q plus 1 minus S minus T, is going to be congruent to Q plus 1 mod 2. And Q, the way we made it, it's going to be a large odd prime. So this will be 0 mod 2. But it turns out that's the only restriction. Given any even number n, if we can apply Rayner's method to produce this E over FQ with n points, then we could find a supersingular elliptic curve, glue the 2 curves together along their 2 torsion, and construct a genus-2 curve with the right number of points. So that is nice, except for this one annoying problem about the thing being even. So we can hope that maybe if we look at n equals 3, which is a little less explicit, but we can deal with it. We're only working over finite fields. It's not that hard a problem. And any time we run into a problem, we could just reapply the elliptic curve construction to get a different prime and try again. And here, if we're going to be gluing along 3 torsion, so now we need an isomorphism of these groups. So now it turns out that we'll get a congruence modulo 3 between these traces of Frobenius. So now n, which is Q plus 1 minus S minus T, will be congruent, oh, and this is 0, to Q plus 1 mod 3. And the one thing you could say about a prime plus 1 is that it's not going to be 1 mod 3. Unless Q is 3, which it isn't, because Q is going to be big. So now, if n is not equal to 1 mod 3, we have a hope of doing this. And it turns out that with a little bit of fiddling, you can write down a supersingular elliptic curve for which you will be able to tie these things together along their 3 torsion. So with n equals 2 and n equals 3, we can explicitly solve the problem for n not 1 mod 6. N factored. I mean, we need n to be factored so we can apply Rayner's method. And if we had explicit constructions for n equals 4 and n equals 5, then we could again do things for n not congruent to 1 modulo some larger numbers. But at least this gives us a solution for 5/6 of the numbers, which is not so bad. So before I give an example, I will give you 2 more applications of these ideas of gluing. What can it be used for? There's a non-constructive question. Given Q, can you give a list of the possible characteristic polynomials of Frobenius of all genus-2 curves over FQ? So these are often called Weil polynomials of genus-2 curves over FQ. And this question is answered now. This was a work. This has been a work in progress for a long time, but the final answer is given in a paper that I wrote with Enrik Nart and Christoph Ritzenthaler that just appeared. And one of the critical cases is figuring out when is there a genus-2 curve with this as its characteristic polynomial of Frobenius. And you can see where this is leading. If you can tell whether or not it's possible to glue two curves together, then you could determine whether or not such a product of Weil polynomials is itself a Weil polynomial. And so being able to look at this gluing construction in some detail and figuring out when it works, when it gives you a genus-2 curve, and when it gives you a split Jacobian is something that we had to look at. So there was one other application of gluing. Another, and this is what the paper with Poonen and Lepervo was concerned with, was constructing genus-2 and genus-3 curves over the rational numbers that had interesting properties. And just to give you an example of what I mean by an interesting property, we were able to write down a particular curve which you can kind of tell from the exponents is obtained by gluing together two elliptic curves. So if you look at this curve, if you look at its Jacobian over Q, this is in a group, the Mordell-Weil group of the curve. And it has a torsion part of order 63, and then it has some free part. I think the rank might be 3, but I'm not sure. I couldn't remember off the top of my head. But so using these gluing techniques, we were able to take elliptic curves that have interesting subgroups and tie them together to get genus-2 curves whose Jacobians have kind of surprising subgroups. You may not immediately think that it would be possible to get torsion of such a large order on a genus-2 curve, but it is. Okay, so I think what I will do to end with, I'm going to switch over to the computer example now. So I have Magma loaded up here with a program that will do the computations to glue together curves with elliptic curve with the right order and a supersingular elliptic curve to produce a genus-2 curve with a given order. This is not an efficient program. It was just kind of a proof of concept, so I can't do large numbers. But I can say let C be the genus-2 gluing of curves that will give us that many points. That is a good... Thank you. Thank you for pointing that out. All right. So initially, yesterday, we were hoping of maybe getting an example with 10 to the 2009 points, but, well, I have code that works for smaller numbers. And actually, it would be nice to verify this, right? So the thing is that computing the number of points on a curve, well, let's see what C is first. Ooh, my screen is too wide. There we go. So it's over a reasonably big field, and I guess now we know that this must be a prime, and given by explicit equations, and we could see how many points this have. And it takes a while to count points on genus-2 curves, at least as implemented in Magma, because Magma doesn't know that this thing has a split Jacobian and that I could just calculate the number of points on elliptic curves. But on the other hand, this should convince you that I didn't get this curve in this program just by looping over curves until I found the right number of points, because that would take too long. And hey, it's right. And if we want something that isn't even, we could say G2, what did I call this, triple? Yes, 2009, 03. We want something which isn't 1 mod 3. So I think that's yesterday. Yeah, okay. Oh, that was fast. So D is that. Actually, and you could see that, well, this one had this suspicious form of only even exponents, so it's a double cover of elliptic curves. This one doesn't have that suspicious form because it was constructed as a triple cover of elliptic curves. And great. So it does actually work, and it was faster to create these things than it was to verify them. So that's good. And I believe that is it. Yeah.
The 63 torsion there, can you see that 63, how it related to the gluing that you were doing? I mean, why were you gluing stuff in order to get 63 torsion?
So we were just gluing things together just to try to get large torsion. And so we took an elliptic curve that had 7 torsion and an elliptic curve that had 9 torsion, and we found examples where the 2 torsion subgroups were isomorphic as Galois modules. So we were able to glue them together using this explicit gluing and get something with 63 torsion.
So how big torsion could you get that way?
The largest Genus-2 thing, I think we had torsion of order 512, maybe? Could that be true? 16 squared? No, that can't be true.
256.
Yeah, so it might have been 128. Might have been the largest example we had. Find the paper. Torsion. Actually, I could go to the introduction to this.
And is it known what the largest torsion?
No, for a Genus-2
even if
curve,
it's
no.
bounded?
No. There we go. So Genus-2 curves, we got various torsion groups and various parameterized families. So I guess the largest torsion group was this one, and it was parameterized by a positive rank elliptic surface. So we could actually get quite a few Genus-2 curves with that type of torsion in the Jacobian. But this is a little bit harder to explain because we start with elliptic curves with 2 torsion on them, and we glue them together, but kind of naively you would expect to lose 2 torsion by the isogeny that goes from the product of elliptic curves to the Jacobian, because there's 2 torsion in the kernel. So we had to do some extra work to make sure that we got torsion back in the end to make up for that. So explaining the 63 case is a little bit easier.
What you show is theoretically possible.
This is what we've achieved. And what's theoretically possible, I don't think anyone knows an upper bound for the torsion on Genus-2 curves.
What are the largest torsion structures known for simple Jacobians?
So Leprevo has a number of papers, I think, where he looks at prime orders, and other people have looked at it as well. I'm not sure what the current state of the art is, but people are getting prime orders, up to 50s and 60s, I think. So, but I don't know what the largest group structure is, the largest torsion subgroup is. Not that I know of. There might be.
I think Stoll had a posting like in the last 6 months or so of a new record.
Okay.
I'm thinking 4 digits, but I can't remember exactly.
Yeah, okay.
So Fock's conjecture, which became Mazur's theorem, right, for the elliptic curves, that grew out of modular functions, right?
Yes.
So there isn't any accompanying conjecture being built in the
there might be, but I'm not up to date on what's been done on this. So. Yeah.
I'm missing something simple. If the Jacobian is a list of unordered points of the curve, how come there isn't a one-to-one mapping between the size of curve and the size of the Jacobian to make the 2 problems more or less equally hard or equally easy?
So so for a Genus-2 curve, essentially a point on the Jacobian is a pair of points on the curve. But that's only essentially. There are exceptions. So there are pairs that become equal to other pairs, and that there's a single point will give you a point on the Jacobian as well. So counting that discrepancy between just square the number of points on the curve and divide by 2, I guess, is exactly the difficulty in figuring out how many points are on the Jacobian. Yeah.
I was going to ask a related question. So can you run this kind of a program for the symmetric square of the curve instead of the curve or the Jacobian?
Say that again. So what do you mean?
So in other words, let's say at question number 4, add to your list, given an n, etc. Can you find a curve, Genus-2 curve, let's say, over such that the symmetric square over f cubed has n points?
Oh. I would think you could do something. I have to, the details are going to be what's going to determine whether it's actually feasible or not. But I think you could probably do something.
Yes, you would need to know about the number of points over quadratic.
Yes, as well as the number of points of the, yeah. So.
But it's closer to the Jacobian than the curve, perhaps.
Yeah. Yeah, I don't know. That's a good question.
Because if you knew that, potentially you could use the alpha Jacobi map and count the number of points on the Jacobian from there.
Yeah, okay, that's something to consider. Okay, all right.